Chapter 14 is about inductance. Inductance is inducing an EMF in a coil of wire or some other device. So we're going to start out by looking at the concept of mutual inductance. The idea here is we have two coils of wire, and the first coil of wire is going to produce a changing magnetic field. The second coil of wire is going to use Faraday's law of induction, or based on Faraday's law of induction, it's going to use induction to generate an EMF, which is going to drive some current. Now, let's just remember what Faraday's law of induction states. Faraday's law of induction states that the EMF induced in a coil of wire with n number of loops is going to be proportional to the changing magnetic flux as a function of time, the rate of change for that magnetic flux. So very importantly, if the magnetic flux is constant, you get no EMF. So just the presence of a magnetic field, just the presence of a magnetic flux does not mean that one coil can induce an EMF in a second coil, okay? Two things are required. One, first of all, there has to be the presence of a magnetic flux through the second coil. And most importantly, that magnetic flux must be changing with respect to time. Okay, so again, your voltage, EMF, is going to be proportional to how quickly the magnetic flux changes as a function of time. So let's take a look at this setup right here. We have a first coil right here, which is going to generate our magnetic flux, okay? And we can see that magnetic field from coil one. Remember, magnetic flux is the integral of the magnetic field over some cross-sectional area. So really, if we're looking at this right here, the magnetic flux would be the strength of the magnetic field, if it were constant, times the cross-sectional area. Okay, so coil one produces our magnetic field. That magnetic field passes through coil two. Now, if the magnetic field changes, that will then induce a voltage in our second coil. Now, we're going to define something here. We're going to define something called mutual inductance. And it really reflects how well a time-varying current in the first coil producing a time-varying magnetic flux through the second coil generates an EMF and thus generates a current, okay? So we are going to call this mutual inductance. And here, M is the mutual inductance of two due to one, okay? And we can see here a few things. First of all, it depends on how many coils of wire we have in the second coil. The more coils of wire we have there, by Faraday's law, the greater the voltage is going to be. Double the number of loops and you double the voltage, okay? It also depends on how much magnetic flux is passing between the two, divided by the amount of current that it takes to produce that magnetic flux. Now, this is a little bit deceiving here because the magnetic flux in this equation doesn't necessarily imply that anything's changing, but it does show that this is how much voltage we will produce per change in current per unit time, okay? Likewise, we can define the mutual inductance of one due to two. That will be based on how many coils of wire one has. In this case, now, if two were producing magnetic flux and it was passing through one, here's how it would induce an EMF. Again, the flux due to that magnetic field divided by how much current was needed to generate that. Okay, so Once again, the mutual inductance of two due to one is going to be equal to the mutual inductance of one due to two. And we can see we can set those two equal to one another. And therefore, there's a relationship between the two. This is going to be important later on. Notice that we've got this ratio of N1 to N2 and I1 to I2, okay? When we talk about the transformer, we will see that the number of loops is very much related to the EMF that's induced. All right, we'll get back to that later on. But this mutual inductance is measured in something called Henry's, named after Joseph Henry, who was an American scientist who independently discovered induction, independent of Michael Faraday. And in his honor, of course, we have named inductance in Henry's. Again, interesting person, lived in the early 1800s. He was the first director of the Smithsonian Museum in Washington, first president of the Academy of Natural Sciences, the first to produce electric current with the magnetic field, and improved the design of the electromagnet, and even constructed and designed and constructed his own motor. So he is the discoverer of self-inductance, which is going to be really very central to this chapter. And again, we have named the Henry H after his discovery, after him actually. Okay, so the EMF developed in either coil is found by combining Faraday's law with the definition of mutual inductance. So for instance, if we have some EMF that we want to look at here, okay, this is a little bit backwards because here we're looking at the EMF in coil 1 due to coil 2. The voltage in 1, because M12 is equal to M21, we'll get rid of the subscripts here, is equal but opposite to M times the change in current in coil 2 divided by time. So again, here we've got to be careful of where the energy is coming from. In this particular case, we are saying that coil 2 is producing the magnetic field, and it's inducing a voltage into 1. Likewise, by symmetry, we could say that the EMF induced in coil 2 is equal to negative M di1 dt. Okay, so either one works. One coil can be the primary, one coil can be the secondary, meaning that the primary is generating the changing field, the secondary is picking up that field. But again, look at what we see in this equation. This allows us to relate, okay, I'm going to get this much voltage due to this change in current as a function of time in the other coil, okay, if I multiply it by this constant M, which is the mutual inductance between the two coils, right? So again, going back to our earlier equation, the mutual inductance was equal to N times the magnetic flux divided by I1. Okay, so this is the mutual inductance in 2 due to 1. And we say that the Henry is how many Tesla times meters squared, okay, or Webers, divided by amps that we get. Actually, I believe this should be amps per second, so got to be a little bit careful there. No, okay, it was per amp. So that's basically looking at the dimensionality of this. I made a mistake there. I apologize. But again, the mutual inductance of these two coils is equal to the voltage generated in one coil due to the change in current in another coil. Okay, so again, that means that Henry is also equal to volts divided by amps per second. Okay, and the better way to really look at this is in terms of this definition right here. Think about mutual inductance as how much voltage I'm going to get for a change in current in the other coil. Okay, this is one of the more difficult sections of physics that I had difficulty with when I was a student first taking this. I had a lot of trouble understanding this whole idea of mutual inductance and inductance. So let me go over some practical applications here. Let's consider two coils. Later on, we'll know that essentially what we've created here is a transformer. And what I want to do is see what happens if I send a current through one coil and how the second coil is going to respond to that. Again, this is a transformer. This would typically have a coil of more wires. Now, that's this bigger cylinder right here. So this we would consider the primary with N1 number of loops. And then the coil, the green wrapped around it, would have N2 loops through it. So the question here is, consider two coils around a central cylindrical area of 1/100th of a meter squared with a length of 0.3 meters long. The inner coil has N1 equals 50 turns. So this cylinder right here has 50 turns, while the outer loop only has 6 turns. Okay, so in a transformer, when you have more coils in your primary, this case N1 has 50 turns. That's where the current is being put into. Then in your secondary, you're typically going to get a lower voltage in the secondary. Again, that's something to keep in mind for the future. If the inner coil has a current of 1 amp, what is the mutual inductance of the two coils? Okay, so we have our magnetic field. We can calculate what our magnetic field is for a solenoid. We had this from the previous chapter on magnetic fields. Okay, so it's going to be mu zero, the permeability of free space, times N1, how many loops we have, times I1 divided by L. That'll give me my magnetic field strength. The flux through the central core is going to be that magnetic field that we've just generated times the cross-sectional area. So that'll be B times A, right? So here, my total flux that is going to be put into this center core is going to be the magnetic field strength, mu N1 I1 divided by L times the area, which is just A. So we calculate that, and we get that we generate a magnetic flux through the core of 2.1 times 10 to the minus 6 Teslas times meters squared. There's your magnetic flux. Okay, now we go to our definition for mutual inductance. Mutual inductance is equal to is a mutual inductance for coil 2 due to coil 1, N2 times phi 12 divided by I1. So we see that at a current of 1 amp, we produce a magnetic flux of 2.1 times 10 to the minus 6 Teslas meters squared. Obviously, if we doubled the current, that would double this denominator, but we would also double the numerator. So here we're sort of looking at the ratio between how much magnetic flux do we get for a given current, and then we multiply that by the number of loops in this secondary loop, okay? So what I see here is, given that I get 1.2 times 10 to the minus 5 henries, or 12 microhenries of mutual induction. All right. So once again, what is a henry? A henry is how much voltage I get for a change in current, a rate of change in current. So for instance, if I were to take, I don't know, a change of 1 amp per second, then my expectation would be in the second coil, I would get 1.2 times 10 to the minus 5 volts of induced EMF. Again, for practical situation, we can see that the second coil will have a voltage. I gotta be careful here. Practical situation, we see that the second coil will have, I didn't multiply by 6. I was a little bit no, I did multiply by 6. So I did multiply by there. So 1.2 times 10 to the minus 5 henries. So again, looking at this, I will have roughly a voltage of 0.1 millivolts for every change in current of 1 amp per second. So if coil 1 went from 0 amps to 10 amps in 0.1 second, now think about that. That's 10 amps in 0.1 second. That's 100 amps per second. Coil 2 would have an induced voltage of 1.2 millivolts. All right. In real world examples, mutual inductance, we're typically dealing with alternating voltage, which is oscillating up and down. So if we think about the way that we would probably input voltage in the primary loop, okay, that function right there might be represented by sine. Now, we know that in the second coil, it's going to, the voltage that we get is going to be not proportional to the voltage of the first, but proportional to the derivative of the voltage of the first. So instead, we would get sort of a cosine out of that. And that's sort of what we would see, that the phase between the two voltages would be different. So where can we see a practical application of this? Well, one place is wireless charging. And with the desire to reduce carbon footprint, reduce the amount of energy that we release, the amount of greenhouse gases we release into the environment, there's been a push to, perhaps electrify mass transportation. We do it already with EVs. You can plug your EV at home and charge up its battery and go to a fast charge station and charge it when you need it. But the problem with mass transportation is that we're talking about heavier vehicles that do a lot of starting and stopping, but we don't want to add a lot of cost and weight with batteries. So one interesting idea is to use buses, which we would wirelessly charge at each stop. There'd be a little primary coil, which would produce an alternating magnetic field. And every time the bus would stop at some bus location, a bus stop, it would get some charge while passengers would come on or passengers would come off. And then the bus could go on its way, and it would constantly be charging during its entire trip and wouldn't need a very, very massive battery. It'd only need a medium-sized battery to do so. Of course, we use wireless charging all the time. One of the problems with wireless charging is we do lose some energy in doing this, but one of the things that's become very popular is to take cell phones and place them on a pad where you don't even have to plug them in, and they simply charge due to an oscillating magnetic field. And again, all these charging pads really are a primary coil embedded in the pad, and then the cell phone itself either has to come with a secondary coil, or you can install a secondary coil on some of these. And this allows the electronic device to charge simply by laying it down on the pad. For a long time, we've actually used this concept of mutual induction for cooking. Induction stoves, as their name implies, have large primary coils underneath them, where this coil will generate an oscillating magnetic field. And the interesting thing is with these pots, you don't even need a coil in the pot. It actually will induce eddy currents within the pot itself, and the bottom of the pot pretty much acts like a secondary loop. And through this, we transfer energy from the primary in the form of an alternating current into the secondary, which is simply just the bottom of the pot. Resistive heating heats up the bottom of the pot, and you've got a nice little primary secondary induction setup right here. So again, if we think about this, the energy input goes into the primary coil. Okay, that's this green right here. The pot acts as a conductor, produces a secondary path for the electricity. So the electricity is transferred from the primary to the secondary. Anything that is not a superconductor has resistance. So that current that is generated in the secondary is going to be turned into heating power, because power is equal to I squared times R. So that's a nice application right there that's been used for quite a long time.